Hi everybody. For those that don't know me, I'm Wynand de Tooy. I am the sales manager for Stormwater 360, and I'd like to welcome you to today's first webinar of the series of webinars that Stormwater 360 is planning to do. We'll do one every second month on topics relevant to the stormwater sector. Today's topic being the hydraulic considerations when designing manufactured treatment solutions in your stormwater network. Our presenters today is Matthew Helms. He is part of our technical sales team, and Matthew's been in industry for 6-7 years now, with experience in drainage design and more recently in stormwater treatment devices. And Kevin Jonathan, whom most of you have hopefully met by now. Kevin's been with the company for ages, years and years. He's our lead stormwater engineer in the team. Also joining us in our Q&A panel is Matthew Murdoch, an engineer in our engineering team. And I think we have the honor of Mike also joining us, Michael Hanna, who is both owner and technical director for Stormwater 360. Mike's been really busy lately with the international leg of the company, where our litter trap catch pit insert is pretty much cooking up a storm as an at-source GPT, protecting the environment in a little bit more of a regulated market, should I say. Just a bit of housekeeping. So please, may I ask that you switch off your videos? It's just bandwidth issues, and mute your microphones. We will give the presenters the opportunity to run through the presentation. And then if you have any specific questions during the session that you would like to remind us of, please use the chat function in the Teams window to type in your questions. I will, during the session, then collate and consolidate those questions. And then if we have time, go through all of them. If we don't, we'll probably go through those that's most relevant to the wider audience. But we will make contact with you to address your specific question that may be more relevant to a design where you need assistance. So I think that's from me. That's it. Thank you very much. Matthew, I'm handing over to you.
Thank you, Wynand. And it's great to be able to talk in a webinar format. So often we are talking about the nitty-gritty details of particular projects with you guys. So it's great to be able to take a step back and look at a slightly higher level around the hydraulics of a stormwater network, and specifically with how that proprietary treatment devices and other treatment devices interact with the network design. So looking at what we're going to talk about, we're going to cover some basic hydraulic principles, and Kevin is going to talk through the specifics around these hydraulic principles and defining them. And then we're going to look at their application of those principles and what that means when you're looking at a proprietary treatment device or a manufactured treatment device. By looking at those and how each principle works with the treatment device, we can then see any issues that if we don't consider, say, driving head or tailwater, what impact will that have on your network if the manufactured treatment device is placed in that network without considering these. And that's quite a key thing, is oftentimes if you approach us for a design, we might ask a lot of questions, and we're trying to make sure that we provide good outcomes for your project. So briefly, we'll look at stormwater contaminants and the levels of treatment that each contaminant requires. Generally speaking, we categorize stormwater contaminants by their particle size. So oils and hydrocarbons we try and divert from stormwater. We don't really want to try and treat that as stormwater. Litter and gross pollutants, generally speaking, is greater than 5 mil. Coarse sediment has a particle size of around 110 micron. Fine sediments, we start getting down a lot finer, and that depends on the particle size distribution of the particular catchment, but typically with a a D50 of around 75 micron, and then we have dissolved contaminants and nutrients. And each of those contaminants has a different level of treatment and layer of treatment that is provided. So typically for oils and hydrocarbons, we look to divert. Pre-treatment, we're looking to capture 100% of litter and trash that is greater than 5 mil. And down to the standard treatment in New Zealand, the standard is around 75% TSS removal. Overseas, it's around 80% TSS removal. So for each of the types of treatment, then there are different types of treatment devices that are designed to provide that level of treatment. So, for example, within the pre-treatment perspective for coarse sediment, generally speaking, we're targeting 50% TSS removal, and that is achieved using a gross pollutant trap, a GPT, a hydrodynamic separator. Within the, say, if we're looking to do nutrient removal, we might have to go towards green infrastructure. That might be a rain garden, a swale, a wetland, a pond, or even a filtera or a bioscape. So within each amount of treatment, each type of treatment, there is a range of devices. Now, within regional council and district and city council guidelines, there are steps laid out for how to design treatment devices. Auckland Council has GDO1, there's the Waikato Stormwater Management Guide, there's the Christchurch Waterways and Wetlands Guide, NZTA, now Waka Kotahi, has a stormwater treatment standard for state highway infrastructure. What is really important to note, though, is that these guidelines lay out the level of treatment that is required and the type of devices that can be accepted. But these aren't based around the hydraulic design of proprietary or manufactured treatment devices. So if the guideline looks at the design of a storm filter, that is for sand filter, sorry, that is from first principles. Looking at the driving head and so on. Same with the rain garden, it is from first principles design of how to design that treatment device rather than a proprietary device. But also importantly, they look at the device in isolation and they don't talk about the integration of any treatment device, whether that is proprietary or not proprietary. They don't talk about the integration of that device into the stormwater network, whether it's from a hydraulic or another perspective. So back in 2016, Kevin and Troy Brockbank, who was with Stormwater 360 at the time, wrote a paper for the Stormwater Conference. And this really addressed some of the questions and some of the things that we were seeing around the fact that these treatment devices use the flow of water and the levels of the water to function. And so the hydraulics and how those devices are integrated into the network is key to their functionality and key to the proper functioning of the network. So the paper that Kevin put together is available on our website, and it goes into a lot of detail about these things. But I'm going to pass over to Kevin now, who will be able to look at some broad definitions for some of the key principles.
Cool. Thank you for that, Matt. So today we're just going to briefly go through some of the basic hydraulic principles that can be applied if you want to design a hydraulically efficient treatment device. Many of you are probably already familiar with this when you're designing a reticulation network. Just bear in mind that designing a hydraulic design of stormwater treatment device is no different to a typical node or junction. So one of them, as you can see on the screen, is a continuity equation, just a simple flow calculation using the byproduct of velocity and cross-sectional area of flow, as you can see. Next is the energy management for flow and pipe. It is basically the total energy upstream equal to the total energy downstream plus head losses from friction. And you can see the graphical representation of that in the presentation. So next is the hydraulic gradient, just defined by the change in hydraulic head or driving head over the change in length, represented by usually by the hydraulic grade line. Can be calculated in either the horizontal plane or vertical plane, as you can see in the graphics as well. So next is the Darcy's law. It is the principle to calculate the driving head required for flow of fluid to go through a porous media. Next is just another application of continuity equation for flow through orifice and also flow through weir. Now, the coefficient of discharge is applied to these equations, but the basic to calculate the flows is still the byproduct of velocity and cross-sectional area. And the most important note here is basically with the same cross-sectional area, if you apply more heat or energy, there'll be more flow. Less heat, there'll be less flow. Next is the head losses. Next one, please, Matt. Which is the head losses that can occur in the network from friction through pipes or bends, T-junctions, and also from exit and entry from hydraulic structures. Now, these head losses reduce the velocity of flow, which in turn increases the hydraulic head required to convey the flow. The graphic on the right shows some of the effect of tailwater to the network and the total headwater upstream of the structure. And this is basically all the basic hydraulic principles that we talked about today. Now we're going to go through and see how these principles get applied when you are designing treatment devices and what you need to consider. Back to you, Matt.
Thanks, Kevin. So what we're going to do is we're going to take some of these principles and take some of the terminology and apply it to our proprietary treatment devices, and we're going to categorize them by the type of device and their general functionality. So we're going to look at on the left is gross pollutant trap, which uses hydrodynamic separation to remove coarse sediment from the incoming water. In this particular instance, we're going to use our cascade separator, GPT, as an example for that. In the middle, we have an upflowing treatment mechanism device. So we're using our jellyfish as the example for this one. And this will be a good example to show how the hydraulics impact on a device where water flows up and through the filters. And on the right-hand side, we've got our storm filter, which is a siphonic cartridge treatment device. And again, by applying these principles to these three different types of devices, you can see some of the impacts that is involved. And it's important to note that we're using these three devices as examples, but there are other devices and it will broadly kind of link together. So when we make a recommendation, when a supplier makes a recommendation for a particular site, we need to understand a few things. We firstly need to understand the treatment requirements. Is it trash capture? Is it coarse sediment capture? Or is it 75% TSS removal? That helps us pick the range of products to look at. We then need to understand the catchment areas and the flow rates, both the water quality flows and the 10-year flows. We need to understand the available depth to invert of both the inlet and outlet. We need to understand if there are any driving head constraints and if there are any upstream or downstream water surface elevation constraints that might impact on the device. So what I'm going to do is pass to Kevin, who's going to run through elevation head.
Cool, thank you for that, Matt. So yes, so elevation heads, more known as a physical drop, is basically the difference between an inlet and outlet pipe invert in a treatment device. And see on the picture, and you probably see in a lot of drawings, there's a requirement difference in inlet and outlet pipe. But it is often misinterpreted to be the total driving head of the treatment device. We have an example here of an image of a treatment device. You can see the physical drop is represented by the delta Z. But the total driving head is represented by delta H prior to bypass or overflow of the system. So if you actually use the delta Z as the total driving head in the hydraulic grade line calculation of the network, you will have an unintended surcharge to your upstream pipe network. If this is not accounted for, it can cause localized flooding to the upstream catchment. So Matthew now will go through some example of this physical drop using a few of our treatment devices.
Thanks, Kevin. So with the cascade and majority of other gross pollutant traps using hydrodynamic separation, this is a cross section through our device, and you can see we have the outlet invert and the inlet invert as shown on our drawings, and the outlet and the inlet invert are at the same level. So with the cascade, with the GPT, there is no physical drop through the cascade. So no physical drop through the cascade. With a jellyfish, again, the outlet invert is shown on the drawings and the inlet invert is shown here. But with the jellyfish, the outlet invert is set relative to the internals, but the inlet invert as standard is 150 mil. But because the jellyfish uses a bubble up mechanism, an upflow mechanism through the filter, there is a range in which that inlet can sit. So that may vary. As standard, it might be above the outlet, but it could, in fact, be the inlet could be below the outlet. So with the jellyfish, we have up to 150 mil physical drop, or the option to bubble up through the jellyfish. With the storm filter, again, the outlet invert is set at the base of the unit, and there is a range of inlet pipe levels. So the outlet invert set at the base, and the inlet invert as standard might be at a higher level, but there is a range where that inlet can sit. And that inlet for the 69 centimeter cartridge storm filter, that could be anywhere between 30 mil to 770 mil fall through the typical manhole storm filter. So you can see that for these devices, the GPTs, gross pollutant traps, the inlet and outlet are at the same level, but for other treatment devices, there is a range of falls, elevation head, physical drop through those devices.
Okay, so in the previous slides, we've talked a little bit about driving head. So now we're going to go through what that is. So driving head, it is also known as a hydraulic head. It is a measure of mechanical energy caused by flow, which is represented by that equation. But it's basically the difference between upstream and downstream water surface elevation. Now, driving head is one of the most very important components to consider when you're designing stormwater treatment device. All stormwater management system requires driving head to operate its treatment mechanism. And without sufficient driving head, it will effectively reduce the treatable water quality flow or the volume it was designed for. And the contaminated stormwater can also prematurely bypass or overflow the device. And as previously discussed, if we don't consider the total driving head, it can cause unintended surcharge to the upstream pipe network. And when it's not accounted for, it can cause the localized flooding. Now, all treatment devices are hydraulically different. They have a different operating mechanism, so each device will require different operating driving head to treat the same treatable flow rate. For example, with a traditional sand filter, used to require about a meter driving head. Rain garden requires about 200 mil of ponding on top. So the driving head is independent to the physical drop through the device. So now Matthew will go through some example of this driving head with a few of our treatment devices.
Thanks, Kevin. So with the cascade, the inlet and outlet are at the same level, and there is, for this, which is this particular device, there is 1.2 meters depth below the outlet invert. So there is a permanent water level within the device. As flows start coming in, the treatment mechanism for the cascade is water flows around, is directed into this central treatment chamber from both sides. So you have two opposing vortices, and then flows out and over atop this weir here. So that is the treatment mechanism of the cascade, and the weir here shows that is then the minimum driving head for that for the cascade. That's for water to start kind of flowing out. What is important to consider, though, is the driving head of a cascade and of any device that uses hydrodynamic separation and weirs to control the flow. Is the driving head the required driving head will be a function of the device size and the treatment flow rate. And if we think back to what the little cross section that Kevin put up earlier, it's the same as designing for a weir. Obviously, if you have a larger device but the same flow rate, your driving head will be less. With the jellyfish, the driving head is shown here on the drawings, and this is the driving head required for the jellyfish to operate at its designed treatment flow rate. So water builds up, comes in through the inlet pipe, builds up behind this maintenance access wall, and starts to flow up through the cartridges here and then through to the outlet. So you can see that then that this is the shown of the driving head for the jellyfish. It is measured from the outlet invert and is typically controlled by an upstream weir that diverts peak flows around the jellyfish. As standard, the jellyfish has 457 mil driving head, but we can go down to as little as 150 mil driving head. However, as we've already discussed, the less driving head you have, the less flow you'll have. So to treat the same flow rate with a reduced driving head, you'll need more cartridges and a bigger device. With the jellyfish, the cartridge size and the driving head both independently affect the flow rates through the device. But it's important to note, with the jellyfish, the driving head stays the same regardless of the inlet level. So if we consider the physical drop through the device, regardless of where the inlet sits on that sliding scale of where the inlet can sit, the driving head will always remain at the same level. So if you have the inlet being lower than the driving head level, then there'll be some, the upstream pipe will be temporarily surcharged. And then with the storm filter, the driving head, again, shown here on the drawings, and the driving head for the storm filter is a function of the cartridge height. As water flows into the storm filter, you can see here there are floats inside each of the cartridges. The driving head is the water surface elevation required within the storm filter for those floats to lift up and the siphonic treatment action to start. So in the storm filter, that is measured from the outlet invert level to the water surface elevation inside the device for the treatment mechanism to start and the device to operate at its designed treatment flow rate. Again, with the storm filter, there are 3 cartridge sizes and 3 driving head options, 770 mil, 540 mil, 380 mil. But again, it's a trade-off. If you switch from the large cartridge to the small cartridge, the treatment flow rate per cartridge decreases. So to treat the same flows, you need proportionally more cartridges. And again, looking at how the driving head relates to the inlet and outlet level, with the outlet and the inlet able to sit on a sliding scale, the inlet sits on a sliding scale, that water surface elevation stays the same regardless of the inlet level. So if you have 69 centimeter cartridges, you'll have a 770 mil driving head, even if you've only got 100 mil physical drop through the device. As a result, then, you will might have some headwater caused by the device. So I'm going to let Kevin run through headwater now.
Thank you, Matt. So headwater, this is also known as back structure. Now, this occurs as a result of downstream obstruction or restriction, such as a weir or orifice, or as Matt said before, a treatment device or mechanism. But this is typically promoted on volume-based device, which relies on low fluid velocity and energy dissipation for sedimentation to occur. Sample of that are ponds or wetlands. And it's also a treatment mechanism that's typically used by hydrodynamic separator, such as the cascade, as previously was Matt said. So an example shown here is a hydrodynamic separator that uses an orifice to raise the water level quickly. So it creates a vortex as its treatment mechanism, and to reduce velocity and promote sedimentation as well. But remember, once you create a backwater, you will surcharge. You start surcharging the upstream pipe. So an example from treatment system we had before, the treatment system had a physical drop of delta Z, and the driving head before the overflow is shown as delta H. So with this example, the system will surcharge the upstream network, and the headwater created by the system is basically the difference between delta Z and delta H, and also further head losses from friction, or if there's further hydraulic structures, it would be exit and entrance losses as well. So now we'll start talking about the tailwater, which is defined as the water surface elevation from downstream of the hydraulic structure. So there's two distinct types of tailwater, which is a permanent and operating tailwater. So the permanent tailwater is caused usually by a permanent pool, typically by a natural water body such as streams, lakes, or sea, or even can sometimes be from submerged network. And the operating tailwater is caused by a depth of flow in pipes or channel, or it can be a detention tank. Now, tailwater condition is an important consideration when you are designing a treatment device, as it can directly affect the available driving head, which can also affect the maximum treatable flow rate and also the operating mechanism of any treatment device. So now Matt will show you how tailwater can affect stormwater treatment devices using some of our system.
So we'll take, for example, the storm filter. And as we've already established, the storm filter, just like all other treatment devices, has a driving head requirement for it to function at its design treatment flow rate. The driving head for the storm filter is measured from the outlet invert level, and that is assuming a free discharge pipe. If tailwater acts onto the storm filter, this reduces the effective driving head of the device. So you can see here in red, we have the tailwater acting on the storm filter. So that effectively then reduces our driving head of the device. So it's a key consideration here, because the water surface elevation for the device to function at its design treatment flow rate has been met. So in the case of the storm filter, the floats have lifted, the siphon action has started, but the driving head is not at the full 770 mil, so we won't get the design treatment flow rate required. So what are the effects then of tailwater? Well, as I said, we reduce the treatment flow rate as a result of the reduced driving head in the system. And as a result, the system can prematurely bypass. So if we've designed to treat a certain flow of water, the system will bypass before we are treating that flow of water. And therefore, the full first flush and water quality flows will not be treated. So it potentially then not achieving the outcomes required as part of consent conditions. If we're designing with operational tailwater, we will need to, just as if we reduce the driving head by going down a cartridge size, we have to include more cartridges to accommodate the reduced flows. One other issue with driving head acting on a device like the storm filter is you can resuspend previously settled out materials, which operationally will lead to issues. From a maintenance perspective, the tailwater, if regular and prolonged, can lead to biofouling of the media. There's risk of the media prematurely clogging, and as a result, requiring more frequent maintenance to that device. Something else that's interesting to consider is tailwater still has to be considered if we're designing with green infrastructure devices. And the hydraulic design of green infrastructure devices is also important. There is still physical drop through the device. There is still a driving head requirement, and the device should be placed offline. And just as with other devices, tailwater will reduce the effective driving head of a biofiltration device. But importantly as well, tailwater and or permanent water can cause nutrient release from organic matter contained within the device. So it's even more important to consider with biofiltration. We're going to look now at the example of our Filtera biofiltration device. So again, with Filtera, we've established that there is a driving head required, and the driving head in the Filtera is measured from the outlet invert to the ponding level of the device. And again, this assumes a free discharging pipe. Tailwater, just as before, will reduce the effective driving head of that device. So you can see here, then the tailwater is effectively reduced. So the ponding level has been met. So the ponding level that we've designed for has been met, but the driving head is not the full 915 millimeters. So we're treating less water. Now, we're fully aware that it's virtually impossible on most brownfield sites and a lot of greenfield sites now to design with absolutely no tailwater in the system. A lot of places simply don't allow it, and I feel for Anton, who's our business development manager based in Christchurch, with a pan-flat city to deal with. Ideally, we want to design so no tailwater acts on a treatment device. However, in some cases, temporary tailwater can be acceptable, but there are some conditions that we look to try and meet. First off is that there's no tailwater during the water quality event, so the 10 mil an hour rainfall intensity. And that is to make sure that at that water quality event, we are treating the full flows and the treatment device is being designed to treat what it has to treat, and we're not going to prematurely bypass. However, flows in excess of that we can deal with, but we try and limit tailwater to at least a 2-year storm event, preferably further, and we have a drain down time of a few hours rather than a few days. If you're designing one of our devices with temporary tailwater, we just say let's take a look at the network design to see if we're going to have any concerns about any operational or maintenance issues. Temporary tailwater for green infrastructure is discouraged, especially for the Filtera. However, there are ways to deal with that with tailwater. We can change the design levels, change the cartridge height, even change the device selection, and look at better integrating into the tanker network design the treatment device. So if we take, for example, a very simple design, catch bit to storm filter to detention tank, we have a discharge invert and a lid level. There is a driving head requirement of the storm filter, but obviously once flows start coming in and restricted by the tank, there will be a tailwater condition placed on the storm filter by the detention tank. So the first option is to change the tank design, either by lowering the tank or reducing the height of the tank. So by reducing the height of the tank, we can remove the tailwater condition from the storm filter, remove or reduce. However, oftentimes that's not practical because you have a council connection that you need to connect to. So the other option is to change the filter design. We can reduce the depth to invert. We can change the cartridge height to lower the driving head requirements, make the unit non-trafficable. So by raising the storm filter up, then we bring the outlet invert above the water surface level in the tank, so reducing the tailwater acting on the storm filter. However, it's at this point we need to look at the network as a whole, because there is still that driving head level within the storm filter, so that could surcharge the upstream network, and we need to make sure that we're not negatively impacting on the structures upstream. So that's a few options for minimizing tailwater, and now Kevin's going to talk through how we manage peak flows within a network.
Thank you, Matt. So yes, a stormwater treatment device can be installed in either an online or offline configuration. So historically, treatment devices is installed in an online configuration. So this is where all peak flows go through the treatment system. However, remember that treatment devices are typically sized to treat only the water quality volume or the water quality flow, but the network is designed to convey the 10-year or even up to 100-year peak flows. So during these higher peak flows, when it goes through the treatment device, it can resuspend the settled sediment, even scarred media and green infrastructure systems, and the peak flow could potentially damage the physical hydraulic structures or even the treatment mechanism. Another biggest important consideration is the driving head required to discharge the peak flow to the internal overflow system. So the way to manage these peak flows, it is to place the treatment device in an offline configuration. This is where only the water quality flow goes through the treatment chamber, and the higher flows in excess of that bypass the treatment chamber. So offline configuration is the best practice for all stormwater treatment device. And now some councils have started to enforce to design all stormwater treatment device to be offline. So the advantage of putting the system in an offline configuration is reducing the driving head required to discharge the peak flows significantly by increasing the length of the bypass weir, and that is a very important consideration for shallow sites to prevent any localized flooding. Again, this is probably quite an important consideration for Anton and Christchurch region. So now Matthew will show you again an example of how to put treatment system in an offline configuration.
Anton's getting a lot of flack in this one for shallow sites, but it's not just Anton. It is across the board as well. So offline design is, as Kevin said, is where we're routing the peak flows, bypassing them around the treatment device. So this is a typical offline configuration. We have a receiving structure and we have the treatment device, and there is a weir in that receiving structure that is set at the driving head level of the treatment device. So water flows into the receiving structure. The weir preferentially diverts flows to the treatment device, but once the treatment device is driving head level has been met and the device is operating at its designed treatment flow rate, this will surcharge, or the water surface elevation in the upstream network will reach the level of the weir, and then flows in excess of the water quality flows will bypass over and around the treatment device. So what does this look like in a long section? So you can see here we have on the left the receiving chamber that has a weir, and then on the right hand side we have a jellyfish, and you can see here that we have the DH, so the physical drop through the device, and the driving head, the design driving head of the treatment device. So as water starts flowing in through the system, it will preferentially flow to the jellyfish, and then the jellyfish will flow. Water will continue flowing to that until it reaches the design treatment flow rate, and at that point, flows in excess of that will bypass over the weir in the receiving structure, ensuring that the treatment device is kept offline and the peak flows don't go through it. Another option, which we're able to do with both the jellyfish and the storm filter, is provide that within one structure. So we have the receiving and bypass chamber here, and the treatment chamber here, and then the peak flow diversion weir sitting in there. Flows coming in are preferentially diverted into the treatment chamber by this weir. Once the water surface elevation has been met for the design treatment flow rate, then water will then bypass over this weir and out, bypassing the treatment chamber. So again, if we compare that to the situation we had before, we still have the receiving chamber and the bypass part of the device. We have the treatment part of the device. We're diverting flows within one structure across that. And as Kevin said, if the driving head is a concern for customized devices, we can look at and make sure that the head losses across that diversion weir will fit in with the network design. So to kind of go back and look at everything and sum everything up, we've gone through some basic hydraulic principles, and we've gone through how they apply, in isolation, essentially, to a treatment device, whether it's a manufactured treatment device or a sound filter or a rain garden or something like that. But again, consider the fact that the council guidelines and the stormwater guidelines out there, they don't look at the integration of these devices into the network. So if you approach us for a design, we will ask you for the treatment requirements. Again, to say, do we need GPT? Do we need full treatment? Do we need something else? We'll look at the catchment areas and flow rates, both the water quality flows to help us size the device and the peak flows to help with consideration around that offline design. We'll look to the available depth to invert of both the inlet and outlet to make sure that we're providing a device that will physically fit into your network. We'll consider if there are any driving head constraints, which will help us select, the size cartridges, the device type, and we'll look at the upstream and downstream water levels to make sure that there's going to be no tailwater or headwater issues. And then we can advise how our devices will integrate into your network. So for relatively simple sites, it could be as straightforward as, here we go. But for ever increasingly complex sites, we can have that discussion and make sure that we're not going to negatively impact. So summing up the presentation, we've gone through some basic of those hydraulic principles: the driving head, elevation head, headwater, tailwater, and designing offline for managing peak flows versus treatment flows. And we've looked at how they impact on proprietary treatment devices. If these aren't considered at that design stage, we can either increase the maintenance requirements of the treatment device. We can not treat the amount of water as required by our consent, or we could inadvertently surcharge the upstream network and cause flooding, which is a pretty serious concern. And for example, Stormwater 360, as a treatment device manufacturer, we're in a position to help integrate our products into your design. And that's a key, is if in doubt, ask. That's what we're here to do, and here to help. So hopefully that covers everything. And thank you all for your time, and especially thank you, Kevin. Vainan, I wonder, are there any questions that have popped through for our team?
Yeah, I've received 2 questions here. Firstly, just thanks Matthew, thanks Kevin. It's it's quite a mouthful, and what I'm learning from this is that there's a lot of complexities, but I think you guys have covered the critical parts of it really well. What I want to say to the rest of the audience is, don't panic, guys. This is why we have an engineering team, is to support and help you with the designs to get this right. So, and really, I think just to reiterate what Matthew said, is that really early on in your design, try and make contact, do the checks. We can help with calculations on the flows. We can look at the hydraulics, the hydraulic impact that the devices can have on your network. So make use of that. It's good sense. There's two questions. The one is on rain gardens. It says the ponding depth in rain gardens are often commented as trip and fall hazards. I think we get that also every now and then. Can you reduce ponding depth and just increase the area? What impact has the reduced ponding level on the functioning? Kevin, maybe that's a good one for you.
Yes, that's a very good question. Yeah, basically, with the rain garden, it is as on one of the slides that Matthew House had before. The basic principle for rain garden is using Darcy's law, and it's basically having the head or driving head over the porous media or the soil. So really, it's that ponding depth is the driving head. So if you want to reduce that, you definitely can. And basically, what will happen is a reduce infiltration rate through the media. And that means you will need to increase the surface media footprint to treat the same flow rate.
Okay, I hope, I'm not going to say who sent that to me, but I hope that answers your question. But you're welcome to make contact again. Thanks, Kevin. The next one was, are you required to manage peak flows outside a treatment device? They all have overflows, right?
Again, that's correct. Each treatment device usually have an inbuilt overflow system. It is based, but it is usually have a limited length on the weir. It's all basically a weir calculation. You're going to have the driving head required to discharge over the overflow weir, and with a limited length, you will require a higher driving head to discharge that peak flow. So again, the advantage of having that offline bypass externally, it can have a much longer weir comparatively to the overflow system. And that means you're reducing the driving head required to discharge over that weir.
Okay, thanks, Kevin.
And I think Fernand, if I may also chip in on that, it also depends. Managing the peak flows will depend on the region in which you are designing. Auckland Council being the only council in the country where you have to divert peak flows around the treatment chamber, they are very clear in their thinking that peak flows cannot be routed through the treatment device and go through the internal overflow. They have to go through a separate bypass weir. Elsewhere in the country, that may be different, but again, best practice is to have the treatment device offline with a separate weir, as that allows you to control that design of the hydraulics of the system much more finely.
Yeah. Let me add from my side also, just for the Auckland-based consultants, council is pretty much clear, especially to us as suppliers. The Auckland Council has approval protocol for treatment solutions in stormwater management, and for our approvals on products that we have to adhere and comply to the requirements for council on the treatment and performance of these devices, they place specific conditions of use. And one of them in Auckland states very clearly that you are not you're not allowed to design a stormwater treatment device online. You have to put it offline. So just make sure that you're aware of that. If you're unsure, then check with your supplier on the specific device approval. That is typically the best place to check. There's a couple of others that came in. Matthew Murdoch, are you here?
I am, yes.
Matthew is in Malamala. They are making our next batch of bacteria media before the whole testing regime starts. Again, thanks, Matthew, for joining us. I think this is one that I want you to answer. Rob Crew has asked, how do you actually ensure that the owner of a device know that they will need to maintain the system, say yearly? It could be that most filters were left unmaintained over the years. Now, while this topic falls outside of today's topic, I think, Matthew, if you can just very briefly maybe explain about the O&M process and just the typical instance here.
Yep, always a good question. We do have O&M manuals for all of our devices, so we will supply those upon selling or providing the product. Myself and our production manager have been working through a contractor maintenance training program. So we will train any contractor that would like to do maintenance on our devices extensively and thoroughly on how to actually go about that process. So that's not just maintenance, that's inspection as well, because we do have a inspect to maintain philosophy that we recommend, whereby you should be inspecting your devices on a semi-regular basis, depending on the particular device. It's also very dependent on the catchment, site-specific conditions. But you should be inspecting the devices early on in their service life to determine how they are going in relation to maintenance and the key triggers that will inform you that maintenance is now required, so that the treatment performance of that device is not impacted. So we've got an extensive training program, and when they sit through that, we will then ask some questions to ensure they were actually watching the content and taking it all in. And assuming they're able to answer those questions, we can then certify that maintenance contractor so that we can say, look, yeah, we're happy that you go ahead and maintain our devices properly, because that is very important that it's done appropriately to ensure best outcomes. But I guess in terms of your actual question of how can we make sure, how do we actually ensure that the owner of the device maintains the system, unfortunately, our influence there is a little bit limited. If you're, say, a car provider, you can't then call up the person who's bought the car and say, hey, you need to maintain your car. There needs to be external forces, so we are kind of looking for council to step in. I know Christchurch City Council is now telling some asset owners that they are aware that they have some devices and they should probably be maintained in the near future. We're also looking towards maintenance contractors. So I know some of the maintenance contractors out there are actually calling up asset owners. They'll find out who has some stormwater treatment devices, call them up and say, hey, you should be maintaining. It's good for the environment. It's good for the asset itself. If it's not maintained, it could do damage to your site. There's a number of reasons why you should be maintaining regularly. So just education really is what it's all about. So that's how we can ensure maintenance is done.
Yeah, thanks, Matthew. Thanks for that. Mike is the saying, typically the stormwater management or treatment devices is typically the most talked about before it goes in the ground and the least talked about after it's disappeared from site, So it is definitely something that you're going to consider. There's also during maintenance, there's some interesting indicators during the inspection. So that is also quite cool. So bringing this back to hydraulics also, when we do inspections into devices, there's oftentimes we can see if there's premature bypassing happening and those kind of things. So it's quite an important regime. But as Matthew said, you can bring the camel to the water, but then we need somebody else sometimes, maybe with the stick, to help out. Okay, cool. I see there's a couple of notes on somebody that's missed some of the record, some of the presentation. We don't have much time left, but yes, we will make a recording of this presentation available that we will send out to the attendance list, but it will also be available on our website, on our webinar page. I'm going to see quickly, there was something about GPTs and TSS. So just go back to how much TSS renew. That was you. How much TSS is removed for your GPTs? Kevin, maybe you want to answer that if you can quickly. We don't have much time left.
Unfortunately, this is probably not a simple answer to go through. It really depends. There has been a misinterpretation or what is with the sediment or TSS. As what Matthew said in the contaminants slide, TSS can range from a very fine particles, down to about 2 micron to about 1 or 2 mils, and basically with the GPTs, there is an approval system that is usually what has been tested to the NJCAT device or NJDAP certification. Now, with these certification, usually they have a preset or pre-manufactured sediment sizes that ranges from a very fine to more larger particles. And if you a lot of GPTs in the market, if they are approved under these certification or program, it has to meet at least 50% TSS removal, and then it will get an approval. But there are a lot of other gross pollutant traps out there in the market that will claim that they remove 80% of 200 micron or 250 micron. And if you only look at the percentage removal and not look at the sediment particle size, you might have misinterpretation to say some GPTs are better than others, while it's actually removing a far larger, or it's being tested to a larger sediment.
Okay. Cool. Yeah, as Kevin said, there's a lot more about gross pollutant traps, and there's a lot of variability on this. And I think best is tap into this resource that you have available. And if there's specific questions related to a specific design or attachment area, feel free to make contact with Kevin and the engineering team. All our details are available on our website, but I think you should have some of our details from previous engagements. I'm just running through this. I don't want to miss anything. Arsini, I see that you've had a quick question.
Yeah, very quick question. Thank you very much for the presentation. It's really good and very helpful. One of my questions is, we usually, from the industrial trade activity perspective, we don't advise applicant sort of like to put this type of devices within the industrial activities. I am wondering, is there any possibility, as far as the engineers are with us, with you guys, to do some alteration to these devices so that we can start sort of like looking to adapt this type of devices within the ITI sites? This is my first question. The second quick question is, you keep saying that it will treat hydrocarbon. It is not clear to me at all, to be honest, how the 360 will treat the hydrocarbon. I believe for the TSS, I believe for heavy metals, but probably we need a little bit more info within your leaflet or within your documentation, so we will understand why, how this can treat the hydrocarbon. Thank you.
Yes. Okay. Just guys, from a time perspective, these are really two very important and good questions. Arsini, I think best is that we'll make contact with you and just discuss this a bit more. It seems relevant to some of the designs that you're currently busy with. In a very brief framework, I want to say quickly, your first question on industrial activity. Yes, you're quite correct. Industrial runoff is not stormwater runoff, but when you apply specific treatment devices in a specific manner, there are ways to target specific contaminants with the treatment train, and this is something that we have done often enough. But typically we would like to have the expertise of an industrial water treatment specialist. Somebody like the IWS group are really good, Jim Maddock there. And he's familiar with the type of treatment devices that you can use. And typically what Jim then does is use differently. You would have like a wedge pit to a gross pollutant trap to a hydrocarbon separator to a fine sediment removal device to something that targets your dissolved heavy metals. So it is really a very specialized kind of thing, but we are getting more versed in that, working in partnership with the industrial specialists. So it is possible. I think make contact with us if you have a specific question or a specific site, and we can refer you firstly, I think, to the specialist in industrial runoff, and then we can work in a bit of a partnership on that one. The second one is, once again, yes, hydrocarbons. It is something that I think from Matthew's slide, the quick and easy is excessive hydrocarbon runoff is not stormwater, and it's not, the stormwater treatment devices are not designed to treat oil out of water. What we want to do is to protect stormwater from hydrocarbons. So in that first one or second slide of Matthew, we had the different categories of contaminants. That first one that spoke to hydrocarbons is we're trying to divert it away from our stormwater, or we're trying to separate it from our water. So there are certain applications where you can try and do that, but you're quite correct. The type of hydrocarbon runoff from something like a standard stormwater perspective, like a car park, there are droplets of diesel, petroleum, the oil coming from a car park. The typical media that can be used can be adapted to target that specifically. There are some absorption quality to that. If we talk about biofiltration, with our Filtera and the Filtera Bioscape, we use a mulch, a matted mulch layer on the top, and that has also some ability for absorbing hydrocarbons coming down. Obviously, not excessive amounts. You know, there's an expected amount coming through our stormwater runoff from roads and from car park areas, so trafficked areas, but anything excessive or anything in risk of a spill needs to be contained and managed separately. But then again, this is not a new question to us. So, and our team's got really good experience in managing that with you and making recommendations on how you can adapt your design to accommodate for that. Okay.
Thank you very much for that quick answer. I really appreciate that. But this needs a lot of discussion. And Jim Maddock is one of my contacts, certainly, because I'm the ITA specialist within the council. So I will follow this up because I'm going to update the PDP of the council. So I wanted to let you know so I know what to put there and what not to put there. Thank you.
Thank you very much, Arsenia. I think you're quite correct. It does take more discussion, especially from a stormwater context. So yeah, happy to follow that up with you. Cool.
Thank you.
So let's see, Aries Consultants, I see is left. Minimum head requirement for our storm filters, needing to meet TSS removal requirement, but working with very shallow stormwater systems. I'm not sure who that was, but it's a relevant question. Quickly, Kevin, if I can put you into that. Do you see the question?
Yes, I believe so. The minimum head required for the storm filters is using our 30 centimeter cartridges is 350 mil. But again, because you have, as discussed before, you have a lower driving head now, so that means you will need more cartridges to treat the same amount of water quality flow.
Okay, so effectively we can meet the performance requirement that is required, but we can make it shallow. And I think, yeah, so just to add to what Kevin had there, we have different size of cartridges to accommodate for more restricted hydraulic sites. And then also the jellyfish that you saw today as one of our case studies or examples that Matthew and Kevin's used is also a device that achieves a certain level of required performance, but can operate at really, really reduced driving head availability. So, and I think that the important message here is that there's a reason why there is a wide range of different treatment devices, even multiples achieving the same level of performance, and it's because of something like hydraulic constraints. So it's really important that you make contact with the supplier to understand what is the available type of solutions for that specific constraint.
I think also Ferdinand, it's important to just clarify that using a smaller driving head doesn't necessarily impact on performance. It's more just the impact on footprint alone. So don't be scared about dropping dropping driving head. Just know that the footprint may very well increase.
Yeah. Thanks, Murdoch. Yeah, that's a good comment to make. I think that there's one more from Julia. Do all of your devices incorporate or need a bypass? From a regulatory standpoint, I'd rather the site flood than send untreated stormwater to the network. For instance, from a lack of maintenance. That is a loaded question, but it is a good one. So let's go and just break it into two things. So the one is, do all of your devices incorporate or need a bypass? So from a regulatory standpoint, I'd rather have the site flooded than send untreated stormwater to the network. Kevin, maybe for you, just to quickly discuss.
Yeah, that's a very interesting comment, actually. I mean, all our treatment system usually have an overflow system, and basically the reason for that is to prevent any flooding during the higher peak flows. Certainly, if you'd rather to have the site flooded than sending the untreated stormwater, we definitely can lose the overflow system. But again, I'm not entirely too sure if other department from council might be too happy, or the site will be too happy with flooding from on the site.
If I can add to that, Kevin, is you know that the reason for the external bypass of your peak flows, Julia, is also, remember what we're trying to do is we want to target that first flush of heavy contaminated water, because that is if we apply the Pareto principle of 80-20, those are 80% of really dirty water, but it's pretty much 20% of that first flow that's coming down. So if you divert that into your treatment chamber, that is the only flow that gets treated, and your heavy or your bypass flows, your excessive flows in excess of your treatment or your design treatment flow rate, is, in a sense, now I don't want to, don't quote me, but in a sense it is cleaner water, because your first flush has gathered and flushed down most of your toxic contaminants down into your treatment device, and then your peak flows then is assumed to come from a cleaner catchment area. And can then bypass. And that way we make sure that we're not scouring and flushing the previously captured contaminants in the treatment device, because that would also be a bad environmental outcome. Maintenance stays the loaded topic here, and the compliance to maintenance requirements, and that is not an easy answer. Maintenance is pretty much, or the operation of these devices is pretty much a partnership. It's a sense of ownership by the asset owner. It is maybe a bit of the stick on the camel. Sorry, Hamish, I saw your comment from council's compliance part, and it is maintenance contractors doing good follow-ups, reminding asset owners, and it is from our side we do have a register of our devices that we supply to the market, and we have a way of following up or sending out reminders, and then also, as Matthew said, the other responsibility that we've taken on is to ensure that the maintenance contractors are trained up so that they are efficient, because efficient also equals more economic in the end. So that is a difficult one to answer, but I hope that the answer about the bypassing is sufficient for you for now. But if you want to discuss further, feel free. Guys, I think that's all we have time for today. There are a couple of extra questions. Thank you for everybody. That's it. Thank you. I'm glad you guys enjoyed it. We'll have our second one in about 2 months' time. We will once again market it the same way that we did this one. So have a look out for that, and hope to see you all next time. Thank you very much for joining us.